So, welcome back. Let us today discuss a very important topic in machine learning known as regularization. Now, if if I tell you so far what we have done, you have assuming that you have some past data and you are trying to um, fit a curve. So, what basically you have done whimsically you have actually designed some kind of predictor, blah blah like that. Okay, and without actually without knowing fully that how this predictor are to be designed from the data itself. Is it possible? Today we are going to explore because this design should be very optimum. Okay, parameters should be optimum, no less, no more, and so that you can best fit your model. So in the again in the context of um, linear regression model, we will learn today that given a data, how automatically you can design your optimum predictor. And in that context, we will talk about regularization, meaning that how to regularize how many parameters will be there in your predictor. Let us take an example, and this example I have made it so it need not be practical, very accurate, but well, for understanding the concept of regularization, I have introduced this example. Say again, housing price. I am trying to create a predictor which will predict the future price of house based on past data. Say these are my past data. This is price of the house number 1, 2, 3, 4, m number of data from the house selling data I have collected, housing pricing data. And say here is a matrix where I have um, I have in a column wise, I have put lots of features. By the way, what are features? Features are important entities which determine the outcome. Here is the price. So one feature could be floor area, number of rooms, number of bedrooms, in which locality it is, conveyance facility, school district. These are actually the features which I have decided, and say accordingly I have collected data. So I have seen one price of a house, and I have measured its floor area, how many rooms are there, how many bedrooms are there, how many dining rooms are there, kind of thing. You can actually you can complicate. uh, and what is the conveyance, school district, is it a good school district or not, because all these parameters are very very important. They determine the pricing of the house. On the other hand, I have incorporated some other features like how much rain you get, pollution level, color of the house. Actually, once you decide in this locality, I need to buy some house. Globally this may be true, but locally if you decide, then a couple of house options are there, and whether you buy a house in this locality here and there, normally the rain, pollution level, everything will be similar. So if you even measure that, they will be unnecessary measurement, and putting them is not going to affect the housing price, but definitely they are going to complicate your model. And if you see, these are my features. If I fully, if I fully clutter the feature space with so many important feature, unimportant feature, or relevant feature, irrelevant features. So I can do that. However, my objective of regularization would be how partially I can determine the features. That means creating some kind of sparsity. We should not be making this column tens. Why? Because you see, in this example again, these are the features, these colored features, they are really, really relevant for determining the housing price. But red colored one, not relevant much, right? Similarly, you can take the example of any medical condition, for example, stroke. So maybe it depends on age, then maybe your uh, means heredity, your lifestyle, those are important features. But it hardly matters whether a particular patient, to collect information, whether a particular patient was fond of it and whether he or she was actually um, social or they were very introvert, all kind of. So those are not very important features when you are determining the possibility that particular patient will have stroke or not. So I think the idea is clear that we would like to uh, parse the feature space as far as possible so that my predicted design, predicted design H parameters by W will not be cluttered unnecessarily with by um, say I decide only to take some um, few features. Okay, so this one, two, three only, I decide that okay, after lot of analysis, I decide only three parameters are good enough for designing the predictor. That would be better. So that is the meaning of cluttering X, uh, as not cluttering much that feature space, rather making feature space sparse. Another question is there a magic which can actually help you? You have only data, right? And you are designing this, nobody else. Okay? So, is there any magic um, which can help you in determining the optimum parameters in the predictor? It turns out yes. Specifically, we'll talk about, without going fairly detailed discussions, we will introduce you. There are three kinds of regularizer. And by the way, they are called regularizer because they regularize the design of predictor. Okay. Uh, one is called Ridge regularizer, another is called Lasso regularizer, another is called elastic net regularizer. Don't worry, I will come back to all this. But before that, I need to introduce the concept of um, what do you mean by overfitting, underfitting a model, and by the way, best fitting. Say I have some data. Okay, so these are my all my data, and I decide I will make my predictor plotted with all kind of possible feature. These are x square, x cube, high order polynomial I will fit so that my curve will pass through all the data which I have collected. Because I do not, I want to make my, after curve fitting, I want to make the error zero. Okay, so and I think that that will be a great design, yeah, because optimum value of the error could be zero, and I have made it. Yes, it is good for predicting in this range where you have collected data, but those are past data. They are useless unless your this predictor is successfully predicting the data trend of the data which is beyond your collected data. Okay, this is the main objective of designing a machine learning model. So, in that context, your such predictor will miserably fail, and technically we call it will fail because it has failed to generalize. There are so many parameters, and it failed to generalize the pattern of the data. That's why it will fail in predicting, because uh, the data after this could be something else, right? And your predictor will not be able to predict them correctly. Means they will predict with huge error. It's a bad design. And incidentally, this is called the curve which you have fit, or the model which you have fit to this data is called, this problem is called overfitting problem. So your model has overfitted. That's why it it will have very poor capability of generalization in capturing the pattern of the data. You see, also we call this is an example of variance, high variance, and low bias. So these are again two term, um, bias and variance, although not exactly in the sense of statistics, but I will discuss what they mean. Bias variance means I am not biased at all, and I have tried to put as many parameters as possible in my design so that I am not biased, and whatever data I have, I would like to fit the data beautifully, keeping very low bias. So this could be a scenario which is bad. Why? Because it will fail to generalize, and actual actual purpose will not be served. Case two, there could be another scenario where you see you have some data, but you don't care about the trend of the data. Well, you decided whimsically, my predictor has to be very simple. Only two parameters I will um, consider, and I will try to fit. I will determine the parameter value through all the techniques which you have learned so far in gradient descent algorithm, uh, or by normal equation. So you will determine and you will try to predict. So this is also very bad design. Why? Because you have ignored the actual train of the data, and you are this call your predictor is highly biased, and it has low variance. Low variance means the model is too simplified, which is it should not be so simple, which will fail to capture the pattern of the data. And as a result of that, in future prediction, this kind of model also will be very bad in predicting. Lot of prediction error will be there. Incidentally, this is called low variance, high bias, and the model is called underfitted model. So it is overfitted. This is a pictorial example of underfitting model. And here, say, suppose you have a data like this, and you have designed a predictor like this, which best fit the model. You see, it may not pass through any of the data. So there will be error for each and every data. Means for each and every feature, what is the outcome? There will be some error, but error will be so small, it is allowable. And this is best fitted curve. Why we call it best fitted? Because in future data prediction, the data for which uh, lying here, data prediction, it will be very good. So this is called best fitted model. So let us try to summarize pictorially what we have discussed so far. We try to introduce the concept of bias and variance. High bias and low variance creates overfitting. Low variance and high bias creates underfitting problem, and optimal bias and optimal variance, which is our objective, is going to give you the best fitted model which will be able to predict. So there is so what is regularization then? And we will achieve this through regularization. In machine learning, It helps better generalization to the new data, saving it from overfitting. It also save model from unnecessarily getting complicated. Model should not be very complicated. That means should not have high variance. Okay, and how we will achieve? So how we will not allow model to be overcomplicated by adding a penalty term, which we will study next, to the loss function, and thereby penalizing the large coefficients. Means we will penalize this kind of higher order terms in a democratic way. We'll take as many as possible features, and associated each feature we will try to design parameters, but we will penalize them so that when the algorithm, regularization algorithm will run, you will see many of the irrelevant features will automatically um, the value of W corresponding to irrelevant features will automatically diminish, or they will vanish altogether, depending on what kind of regularization technique we are using. Also, regularization try to strikes a balance between model bias and variance, leading to improved performance. So, specifically, we'll discuss here three different kinds of regularization techniques. One is called reach or L2 regularization, which was proposed, you see, way back 1940s by Andrei Tikhonov, a mathematician from Moscow State University, and is a very popular regularizer even today. And the reason I will tell you why it is popular. Then we'll talk about also Lasso, list absolute shrinkage and selection operator. This is the abbreviation Lasso regularizer or L1 regularizer. Since it is completely iterative in method, and optimization requires a lot of iterative method, which are computationally not very friendly, but nevertheless, from 1996 onward, the Lasso concept is picking up, propagated by Robert um, Tipsirnadi, and it is recently gaining momentum because we have computational muscle powers nowadays. And another regularizer, which is elastic net regularizer, which takes best of both the regularizer reach and lasso. Now let us try to tell you what they are, and how they can be incorporated. So this is our loss function. Loss function you have already designed. Um, I equals to 1 to m. So that was your loss function j, wj. So the suffix j stands for wj, j stands for uh, features, and I stands for some number of samples. J equal to say 1 to up to n, and I equals to 1 to up to m. M is the number of samples. So this was your loss function, and the function was very beautiful in the sense that it was perfectly uh, if I take one feature, I have shown you, you now know the nature of the function is convex, okay, quadratic in nature, and it is beautiful because it has only unique optimum point, right? So running gradient descent algorithm will fetch W corresponding to this point, okay, and you will collect those W's and plug in to your predictor. So that was what you were doing so far. Now, what if we try to add another term, which is um, penalty? with a penalty. Lambda is a penalty term, and you have added another term here. So your objective function now becomes the least square objective function plus a penalty term, which we call a regularizer. Now let us see what it is doing. Okay. By the way, you will know, actually, uh, we have um we have a theory behind it, why we did it actually, and I will discuss it when we will discuss some vector machine in detail. So this is called Lagrangian optimization method. So it has, say, um, zeta is some constant. So suppose it has some kind of constraint. Okay. So Wj squared, summation of Wj squared, j equals to 1 to n, must be less than equal to zeta. And I need to optimize this objective function subject to subject to this. So this can be done by adding a Lagrangian multiplier lambda, actually, which we are calling it penalty term, and taking this here, it can be written summation of j equals to 1 to n wj squared minus zeta equals to 0. And then since zeta is constant, we are not writing it here because they will play no role in differentiation. It's constant, so differentiation with respect to w will vanish. It's independent of w. So actually, uh, adding this has a ramification, has a greater meaning, that we are trying to optimize with a constraint, which is a regularizer. Okay. Mhm. Now, in doing so, what we have done, I will I will tell you what we have done. You see, so this is my modified. So we are talking about L2 regularizer. So this is my modified objective function. I would like to now run gradient algorithm with this kind of function, that mean least square error function plus a regularizer term attached to it. So first term we do not regularize. It's not needed because we have only fictitious um, parameter x0 here. Okay, so normally we do not regularize it. It is a bias term, and other term we have this. So new assigned value wj equals to earlier wj minus c, this alpha, and derivative of this function. So you differentiate this function and you will get this one, as you know. This is for least square function, and this is for the uh, regularizer term, isn't it? Just differentiate, you will get it. And this differentiation already we have discussed in my earlier lectures. Okay. So everything is clear here. Alpha is the learning rate, m is the number of samples, lambda is actually penalty term, which is again um, uh, we will select a hyperparameter. So these are the things. Now you see, just a little bit algebra, if you make, then you see the wj is always multiplied with a term 1 minus alpha times lambda divided by m minus this. So what is going to happen if m is large? Then for a fixed lambda and alpha, this, so always, first of all, always this parameter is less than 1, isn't it? So this is a fraction, and this is some value selected by you, and normally this is high enough to make it a fraction. So 1 minus a fraction value is a fraction. Okay. So now if m is small, then what will happen? That means you do not have much complicated pattern in the data, right? So you don't need so many parameters or features to be associated in your predictor. So what will happen as you will run your algorithm with the given data, this term will annihilate many of the W's, okay? And only, and you can see, although they will not make them zero, this is another observation. L2 regularizer will not be able to make your um, vanishing or W parameters. However, substantially the W value will be diminished. Some of the W values will be faster diminishing, and now judgment is yours. You know that suppose I am designing originally W1 x plus W2 x2 square x square plus W3 x square plus W4 x4 square. So originally, suppose I am running with the data, I am running gradient algorithm to this predictor for determining these parameters. Okay, so there will be how many loops? One, two, three, four, five loops will be there, which will run, and they will give you five parameters. Now this term will try always to annihilate Wj if they are not required. And you will see if the data is such that it does not require some irrelevant features like this and this, say this and this, it is not required. So what you will get, substantially you will get W0, W1, W2 values when it will converge, and you will get very less value. I'm giving an example, okay? W3 very less value. W4 will converge to a very, very less value, small value. So now choice is yours. You can ignore them completely. So this is the role regularizer is playing actually to give you a control and you to decide that how beautifully you can mm, you can optimally you can design the predictor. Now, in case of lasso regularizer, we do the similar kind of thing, but instead of this, we put Wj, j equals to 1 to n. Now, in putting this penalty lambda, which is directly multiplied with the parameter, you cannot so easily um, differentiate because Wj is squared is not there, so it will vanish. Okay, if differentiation if you do, but nevertheless, this is still a quadratic. Uh, this is still a quadratic function, and like using same Lagrangian principle, you can actually regularize your objective function. However, running gradient algorithm as an optimization as an optimizer will not work here, as I told you, because there is no this term. Okay? So what we do, there are so many algorithms. I can just tell you uh, some of the this is uh, you do not if some of you can actually are interested to see that in this paper, it's very recent paper, March 2023, the authors have actually archived it, a survey of numerical algorithms that can solve the Lasso problem. So you will have to go to the numerical solutions, and one such solution technique we will study when we will study support vector machine, which is known as coordinate ascent algorithm. But here I would like to highlight, though, that it is possible. It is possible that you can incorporate lasso regularizer, and you can regularize your predictor. That means you can design your predictor optimally. So this is another good pictorial view. It shows it's why it is important. You see, this is model complexity versus bias and variance trade-off. See, this is the bias. So the when the bias is um, increasing, bias is increasing towards this, and model complexity is decreasing, but error will also increase. Okay. On the other hand, when variance is increasing, there also the error will increase and the model complexity will increase. Here, with this variance, model complexity is simple. In this zone, it is simple, but error will be, so total error will be large. So what we need to do, we need to optimally make my model complex so that the error should be in this zone, neither here nor here. So that is bias variance trade-off. So we were discussing, and I have told you that how actually the regularizer work. Actually, it helps you optimizing the parameters. And here pictorially, and I told you that although I have shown you how it is working in case of ridge regularizer, as you have seen, that Wj will annihilate or will diminish as the iteration goes on for a particular data set. Here the data will determine which W will remain, which W will be insignificantly determined. Suppose I told you some W parameter, say W1 is become substantial, W2 become also substantial. But how about W3? If your algorithm settles W3 at 0.001, W4 in 0.00001, and you have designed this kind of things, W0 x0 plus W1 x plus W2 x square plus W3 x cube plus W4 x4, like that. Hypothetically, you say you have designed a predictor like this, and adding the range regularizer or L2 regularizer, you have got as a result of running gradient descent algorithm, as a result of parameter determination convergence, you got this converged value. You can really ignore this and this, because those are not the important features. So that's how your ridge regularizer works, as I told you here with two example. Uh, this is a constraint. So underneath, this is nothing but Lagrangian method of optimization that you will appreciate when you will study support vector machine again. So this is my least square error function. You see, this is the red one. And if you just make the least square error function optimum, then you will get W here. But when you put the constraint, these are lasso constraint. So lasso is actually, I told you, say another term. Okay. So this is what, okay, let us put it here. Zeta is a constant, right? So that means this is your, so for feature, feature, you have W1 plus mod of W2 less than equal to zeta. So you can, in Lagrangian multiplier method, if this is an objective function subject to the constraint, so how to optimize this objective function subject to the constraint? Now we are putting a constraint here. And pictorially, the constraint is a mod W1 plus W2. It will look like this, plus 12, drawing plotting mod function. And then satisfying this constraint, your optimum value will be either this, or if this touches here, optimum value could be this, like that. So what is happening here? This is, although very simplified way of showing you, only one is remaining. This is gone. W1 is gone, right? Eh? So this is W2, 0. So one parameter is already gone. So this is a simple example which shows Lasso has the capability by the process of solving optimization problem using Lagrangian method or some other method you can apply. So it is constraint quadratic optimization problem. If you solve that, then Lasso has the capability of completely removing or eliminating some of the parameters. On the other hand, in reach regularization, you can see it will always, so it is, this is actually the equation by the nature of the Lasso penalty term. The constraint is actually a circle. The how big circle will be, that is different issue. Here also how big this will be a different issue. Okay, so it is touching means those, now these are this objective function, this is constraint. So satisfying that constraint, the new optimum values will be this. Here, both W1 W2 will always be there actually. And all the objective points will be lying here, not here or here. Okay. So that's the difference between Lasso and Ridge. So in short, Ridge regularizer, although will not make any of the parameters um, value 0, it has the capability of diminishing the value based on data, um, whereas Lasso has the capability based on data to completely annihilate some of the parameters. Now choice is yours that what to use, and that's why we use, and we do not know, right, that whether it is good to completely remove some of the parameters or it is good to put them with uh, lower values. So that's why what we do, we, as I told you, we try to put both L1 and L2 regularizer in my objective function. So this is my least square objective function, and two constraint we have put here. See, lambda, lambda dashed. Lambda corresponding to ridge regularization, lambda dashed corresponding to Lasso regularization. So this kind of constraint objective function, if we optimize, and in that process we will get W values, those W values will be optimum one, because some of the irrelevant W's completely will vanish, some of the W will have their diminished character or improved character. So you can see what W actually is surviving after iteratively determining, solving this optimization problem. That means determining parameter Wj is. Is it clear? I think it should be clear, and that in that way you can have your predictor keeping only the relevant parameters associated with relevant feature. So automatically the parameters associated with rain kind of thing. This is a very uh, very vague example, simple example. So if I just really collect the data and if I try to run my regularizer here, you will see, because I am using elastic net regularizer, so completely some of the parameters associated with rain, pollution control, color, they will completely vanish, and not so important will remain there. For example, number of bedrooms, number of dining rooms, number of this room. They are sometimes redundant. Okay, so the parameters associated with such kind of feature, their value will come, will try to diminish, and then it is our choice that whom we should finally select in designing a predictor which will predict beautifully my unknown um, data, right? So this is the concept of a regularizer. Okay, and in case of normal form of equations, recapitulate. We have discussed how to determine this parameter, and simply we put here the a regularizer term, which is a penalty lambda times a identity matrix, which will save this um, for calculating the determinant of this matrix, which will save it from singularity. Because by virtue of selection of non-zero lambda, it will never allow the determinant to be zero. Okay, so this is the effect of regularization which it has in case of normal equation. But frankly speaking, where everywhere the regularization important is mostly important when you are trying to solve using iterative method. So I will just conclude by discussing about how actually predictors can be designed. Suppose you have now original data. So normally we split the data into two set, training and testing. Now within training set also, we perform k-fold cross validation. Why? Because we want best fit model, and that best fit model will not come from the heaven. So we'll have to regularize, we'll have to iteratively design. So validation, k-fold cross validation is a technique which you are now learning, you see. So what it does, within training set, suppose I have 80% data in my training set and 20% I have kept for, um, so 80% and 20% I have kept for testing. Now within this 80% data itself, then again I keep say 80% of 80% for training and remaining 20% for validation. That means if you are having 100 data, so 20% of 80 means 16 data will keep out of 80, 16 data you will keep for validation, remaining for training. And then whatever running this regularizer algorithm, you um, optimize the parameter and keep them. Okay, and they will give some error. Also calculate the square error, which is actually a metric. How beautifully you have designed your predictor. So put it there, and then in first iteration you do and set of wj and e you keep. In the second iteration, what you do? Those who were in the validation set earlier, you allow them to act in the training process and select the 20% from the remaining, earlier remaining training set, 20% for validation. Okay. And you see this validation set is now training set, and this is a new kind of validation set which we have selected, and then repeat, collect this. Like that, you k-fold means you have decided you will run fourth iteration. It depends on your choice and data. K-fold, that's why it is k-fold. What will be the value of k? 4, 5, 6, 100, 10? That is your choice. And more you do it, more computation you will have to do, and more option you will get. And you can see, since you are simultaneously collecting your set of W corresponding to the error, square error, you can see that which set has given minimum error. And you can, and it's good idea actually to finally design, it's good idea to democratically give weightage to all the W's in your predictor. Please do not eliminate, because then you may ignore some useful pattern. Okay, so this good idea is just democratically select all the W's. However, give proper weightage. If some set of W has very less error, give it more weightage. Other, and like that chronologically. And then finally, you design your predictor. Then you can test that predictor, and you will see um, whether the performance, that means in terms of error, um, performance is good or bad. If the performance is not so good as you desire, then again come here and make the k number 6, do the same thing. So in this way you can just try to um, explore the data uh, more um, transparently in designing your predictor. So the um, reference of this picture can be is here. So with this, I think I will conclude. So you have learned today that what is regularizer, and in the context of machine learning, how regularizer is useful for designing a, uh, an optimum predictor. Thank you for your attention, and I will now define some assignment which will require for digestion actually, and which will require to implement all the things which I have discussed today. Bye bye. Have a nice day.